Natural language processing, the field that enables computer to understand human languages, has been significant advancements in recent years, thanks to deep learning techniques such as recurrent neural networks and their variants, including long short-term memory. However, while this long short-term memory have shown impressive results on various tasks, they still feel challenges related to accuracy and capacity, especially when dealing with long sequences or rare events. So to address these issues, researchers have developed xLSTM, that is a new architecture which is designed to improve both performance matrices while maintaining computational post. So today we will understand what exactly this xLSTM is, how it differs from traditional LSTMs, and why you should consider adopting it in your next NLP project to supercharge your apps. So let's get started and stay tuned for further insights. Now, what is LSTM? Basically, this LSTM stands for long short-term memory, which is a type of neural network that can remember important informations over a long period of time, like our own human memory. It helps computer understand and recall complex relations between pieces of information presented over time. So this long short-term memory uses gates, which is input, output, and forget gates that decide what to remember, what to discard, and what to pass forward respectively. And by doing so, long short-term memory can handle sequence of input data like text or audio and make predictions based on the patterns found in those sequences. For example, when speaking, our brain uses LSTM-like mechanism to store the underlying meaning of words despite changing duration and intonation patterns. So overall, this long short-term memory enables more efficient and natural language understanding and generation in NLP applications by helping to predict the next word in a sentence given the previous ones. But if we have LSTM, then why we need the extended version of LSTM? So this xLSTM is necessary because regular long short-term memory networks have some drawbacks. First, they find it hard to update old stored values when looking up a particular vector via nearest neighbor search due to an inability to revise storage decisions. And this problem is solved by exponential gating in xLSTM. Then LSTM struggle to store vast volumes of data, especially uncommon or seldom used tokens, because it packs everything into tiny scalar cell states. So this xLSTM will tackle this issue by incorporating a matrix memory and completely parallelizable modifications. Then lastly, the connectivity structure between hidden layers inside LSTM makes scaling challenging, which limits its usage in gigantic language models. So this xLSTM solves this restriction by foregoing memory blending in favor of total parallelization in its matrix memory form known as mLSTM. So overall, these enhancements offered by xLSTM allow it to perform better than conventional LSTM networks under certain circumstances. Now let's understand this xLSTM. So this xLSTM consists of two major variations. First is your scalar memory and scalar update with memory mixing. Then it has matrix memory and covariance update with no memory mixing. So by incorporating both into this residual block modules, researchers can develop xLSTM blocks that can be stacked in architecture for improved performance. And these advances allow us to surpass the limitations of traditional LSTM networks and scale up to match the capabilities of contemporary large language models. So to understand this better, let us say you want to create a model that can read a novel and accurately predict what comes next. So that is where LSTM and xLSTM come in. So imagine each sentence in the book being a step forward and every word within that sentence being a single unit in our model. So now let's look at how both LSTM and xLSTM will handle remembering all those previous steps. So let's start with first LSTM. So LSTM will remember important information across many steps, but sometimes forgets critical details along the way. It is like trying to remember a list of numbers while also juggling multiple balls. You might drop some crucial digits before reaching your destination. Then enter xLSTM, which builds upon LSTM to provide a solution. So essentially, xLSTM breaks down the process of remembering sequences into simpler building blocks called residuals, which allow it to distinguish better between various events and context. And each residual will summarize the history of previous steps in a high dimensional space, which makes it easier to tell apart related information from irrelevant ones. So with xLSTM, it's like having a virtual assistant besides you to keep track of what's all is relevant information without losing sight of essential details. So when working with this complex data, such as long novels or scientific papers, xLSTM helps ensure greater precision and reliability compared to traditional LSTMs. Now understand what's the difference between this LSTM, then xLSTM and mLSTM. So LSTM, it stands for long short-term memory, which uses a single type of memory called a scalar memory to store information. And it has 3 gates: input, output and forget gate to control what gets added or removed from its memory. So however, LSTM struggles to efficiently store and retrieve infrequently occurring words because it compresses all information into a single value, which limits its storage capacity. Then comes the scalar LSTM, which is an extension of LSTM that improves upon its limited storage capacity. So like this LSTM, scalar LSTM also utilizes a scalar memory, but instead of just one update, it allows multiple updates with exponential decay factors, which provide greater flexibility in memory management. So additionally, this xLSTM includes a memory mixing mechanism that combines memories from different time steps to better retain important information. Then comes this matrix LSTM, which takes a fundamentally different approach than LSTM and scalar LSTM by replacing the scalar memory with the matrix memory. So with the matrix memory, this mLSTM can handle much larger volumes of information due to its increased dimensionality. So moreover, instead of using the traditional dot product update operation, this matrix LSTM employs a covariance update, which allows for efficient and parallelized computation. So while this mLSTM does not use memory mixing, it still benefits greatly from exponential gating, which helps to preserve critical details during training. So overall, while LSTM was a significant breakdown in neural network research, the scalar LSTM and this matrix LSTM built on top of that foundation to address some of its fundamental limitations, improving its efficiency and versatility in handling complex sequences. Now understand the architecture of this xLSTM. So essentially, this xLSTM is a way to improve the accuracy of predicting future sequence elements, especially for long inputs. And it does this by breaking down the process into smaller building blocks, which is called residuals, which summarize the past in a high dimensional space to help differentiate between different events or context. And these blocks are stacked together in what's called xLSTM architecture, following principles from math theory called Cover's theorem, which essentially says that distinguishing between distinct histories require embedding them into high dimensional space that allows linear separation of patterns that might not easily separate into lower dimensions. And by doing so, it allows us to make more accurate prediction for longer inputs, allowing further optimization may still be needed for extremely long inputs over roughly 16,000 characters. So overall, this xLSTM is a powerful tool for improving the performance of machine learning models for tasks involving sequential data. And in comparison to transformer models, xLSTM networks have a simple calculation process and a predetermined storage requirement dependent on input size, making them beneficial for practical implementations and gadgets with restricted resources, such as cell phones. So despite not requiring any additional parameter setting for internal memory storage, this operation may prove pricey, owing to multiple matrix multiplications equivalent to the quantity of concealed devices. So this is this LSTM, then comes the xLSTM, and then we have a mLSTM. So here we can understand in this LSTM we have sigmoid gating, recurrent inference, recurrent training. In the scalar LSTM, we have an exponential gating. And then this matrix LSTM, we have matrix memory, parallel training, covariance update rules, which makes it better than LSTM. Now let's take a simple Python code for better understanding. So here is a Python example. We shall implement this long short-term memory network using this Keras library. So here first of all we have imported NumPy Keras model, Keras layers, and loaded the data set into NumPy array, which is called dataset. And then we extract xtrain and ytrain. Next we defined the architecture using the sequential class in Keras, and each layer is stacked sequentially using this add function. So first we are using the embedding layer to convert each word in the input sequence into the dense vector representation. Next we use two LSTMs with a total of 128 memory cells each to learn long-term dependencies in the sequences. And finally, we use a fully connected layer with a softmax activation to produce probabilities for the output classes. And we compile the model using compile function, specifying the loss function, that is the categorical cross entropy optimizer is Adam and batch size is 32. Finally, we train the model using this fit function, which is provided by Keras, passing the input data, target values, number of epochs which are 50, batch size 32, and a portion of the training set reserved for the validation, that is validation split is 0.2. And after this training process completes, the history object contains various matrices calculated at the end of every epoch, including accuracy, loss, etc. And these values can be accessed later through the history dictionary returned by fit. Just note one thing, that you will need to replace your data file, that is your data file.npi, with the path and file name of your data set. So additionally, you should modify the hyperparameters like input dimensions, batch size according to your specific used case. Thank you.